Tonight, we'll be exploring the fascinating story of ancient astronomy and discovering the remarkable ways our ancestors tried to understand the universe. Long before modern science had a name, people were already asking serious questions about the heavens. They noticed that certain movements returned with surprising precision. And over generations, those observations became systems of knowledge that could shape entire societies. Ancient astronomy reveals the true ingenuity of humanity, even in times without advanced technology. With patience alone, early astronomers measured cycles that stretched far beyond a human lifetime. Their records preserved events that modern researchers can still study today. Some of their conclusions were remarkably accurate. Others were shaped by ideas that later science would overturn. But all of them mattered, because every attempt brought humanity closer to seeing the universe as a place governed by patterns we can understand. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is get settled in. Let your shoulders soften, let your breathing slow, and allow your mind to settle into stillness as we embark on this fascinating journey through the ancient sky together. Let's begin. Ancient astronomers predicted eclipses long before telescopes existed. In the ancient world, patient observers learned that these events followed patterns. They did not need glass lenses or space probes. They needed memory, mathematics, and generations of records. Babylonian scholars were especially skilled at this. By watching the moon over centuries, they noticed that eclipses often returned in a repeating cycle now called the Saros. It lasts a little more than 18 years. After one cycle, the sun, earth, and moon come close to lining up in a similar way again. This did not make every eclipse easy to predict for every location, but it gave ancient astronomers a powerful warning system. Imagine living in a world where the sun suddenly dimmed, and yet someone had already expected it. That ability must have seemed almost impossible. It shows that astronomy began not with machines, but with careful eyes and inherited knowledge. The night sky was humanity's first clock, map, and calendar. Before written schedules, mechanical clocks, or printed maps, the sky gave people a dependable way to organize life. The rising sun divided day from night. The moon offered a visible rhythm that changed across a month. The stars returned in familiar patterns as the seasons turned. For early communities, this was not a distant hobby. It affected survival. A bright star appearing before sunrise could signal that rains were coming. A certain constellation in the evening could tell hunters or farmers that a familiar season had arrived. Travelers used the sky to hold direction when landscapes became confusing. The heavens became a shared system that every generation could learn. It was above every village, every field, and every shoreline. What makes this so remarkable is that the sky was both beautiful and practical. It helped people plant food, hold ceremonies, measure time, and move through the world. Long before astronomy became a science, it was already part of everyday life. The Great Pyramid aligns with the cardinal directions astonishingly well. The Great Pyramid of Giza is not only famous for its size, it is also remarkable for its orientation. Its sides are aligned very closely with north, south, east, and west. The builders achieved this more than 4,000 years ago, without compasses, satellites, or modern surveying instruments. That precision has fascinated researchers for generations. One likely method involved watching stars near the northern sky, especially stars that circled around the pole and never set below the horizon. By observing pairs of these stars as they moved, ancient Egyptian surveyors may have found true north with impressive accuracy. Another possibility involves careful solar shadow measurements. However they did it, the achievement shows that monument building and astronomy were deeply connected. The pyramid was not placed casually in the desert. It was fixed into the order of the heavens. Stone, geometry, and sky became part of one design. Its alignment reminds us that ancient engineering often began by looking upward. Ancient Chinese astronomers recorded supernovae that modern science can still identify. A supernova is one of the most violent events in the universe. But to ancient eyes, it could appear as a strange new star. Chinese astronomers were among the best record keepers of such events. They called these sudden lights guest stars because they arrived in the sky, stayed for a while, and then faded away. Their records often included where the object appeared, how bright it seemed, and how long it remained visible. One famous observation from the year 1054 describes a brilliant guest star in the region we now associate with the Crab Nebula. Today, astronomers know that nebula is the expanding remnant of a stellar explosion. The ancient record helps connect the object we see now with the event that created it. That is astonishing. A court astronomer writing with brush and ink helped modern scientists understand a cosmic blast. Across nearly 1,000 years, one careful note became evidence for the life and death of a star. Greek thinkers realized Earth was round by studying shadows. The idea of a spherical Earth was not guessed from space, of course. It grew from observation. Greek thinkers noticed things that did not fit a flat world. During a lunar eclipse, Earth's shadow on the moon always looked curved. Ships disappearing over the horizon seemed to sink hull first, rather than simply shrinking evenly into distance. Different stars appeared as travelers moved north or south. These clues pointed toward a globe. Aristotle argued for the roundness of Earth using several of these observations. Later, others refined the idea with measurement and geometry. The brilliance of this discovery is that it came from ordinary phenomena, carefully interpreted. A shadow on the moon became a clue about the shape of the world. A ship on the sea became evidence for curvature. This was one of the great leaps in human thought. People realized that the ground beneath them was not an endless plain. It was part of the vast sphere suspended beneath the sky. Polynesian navigators crossed oceans by reading stars without instruments. Across the Pacific, skilled navigators made voyages that still inspire awe. They crossed enormous distances in canoes, often without written charts or metal tools. Their knowledge lived in memory, training, and practice. Stars were central to this art. A navigator knew where important stars rose and set on the horizon. Each star could act like a direction marker. As the night changed, one guide would descend and another would take its place. But stars were only part of the method. Navigators also read ocean swell, wind, bird flight, cloud shape, and the behavior of light near islands. The sky worked together with the sea. This knowledge was not vague instinct. It was a disciplined system passed from teacher to student. To sail this way required concentration beyond anything most of us can imagine. The navigator became a living instrument, holding an entire ocean in the mind. Ancient astronomy was not always written in observatories. Sometimes it traveled across water under a moving canopy of stars. Stonehenge may have helped mark solstices thousands of years ago. On Salisbury Plain in England, Stonehenge still stands with a presence that feels deeply intentional. Its great stones were arranged long before modern astronomy, yet the monument connects powerfully with the sun's yearly cycle. At the summer solstice, the sun rises near the direction of the heel stone when viewed from the center of the monument. At the winter solstice, attention may have focused on the opposite direction, when the sun sets at its lowest yearly point. Archaeologists debate exactly how the site was used, but the solar connection is hard to ignore. For ancient communities, the solstices mattered. They marked extremes in light, turning points in the year, and moments when seasonal expectation could become ceremony. Building such a monument required labor, planning, and shared purpose. Its stones were not simply lifted for decoration. They shaped experience. People could gather and watch the year turn in the architecture itself. Stonehenge reminds us that ancient astronomy was often public, physical, and deeply communal. Ancient astronomy turned the sky into a guide for civilization itself. When people learned to read the heavens, they gained more than knowledge of distant lights. They gained a framework for organizing society. The sky helped rulers choose ceremonial dates. It helped farmers prepare for seasonal change. It gave priests a structure for ritual life. It gave travelers confidence in unfamiliar places. Because celestial patterns seemed stable, they offered a sense of order in a world filled with uncertainty. This made astronomy useful to cities, temples, courts, and farming villages alike. It also encouraged record-keeping. Once people believed the sky mattered, they had reason to watch it again and again. Over time, those observations became calendars, predictions, myths, mathematical tables, and monuments. The study of the heavens became one of the foundations of organized culture. It linked practical needs with deeper questions. What is time? Where are we? What power governs change? Ancient astronomy did not merely explain the sky. It helped humans build meaning, authority, and rhythm into life on Earth. Babylonian astronomers divided the sky into zodiac constellations. The zodiac began as a practical way to follow the paths of the sun, moon, and planets. Babylonian astronomers focused on the band of sky, where these bodies appeared to travel. They divided that region into recognizable sections associated with constellations. Over time, these divisions became a powerful reference system. A planet could be described by its position within a certain part of the zodiac. This made records clearer and predictions more systematic. The familiar names later passed through Greek astronomy and eventually into wider tradition. Today, many people know the zodiac mainly through astrology, but its roots include serious sky measurement. It was a coordinate system before it became a cultural symbol. The Babylonians needed a way to describe a moving heavens with accuracy. By giving structure to the apparent road of the planets, they created a lasting map of celestial motion. Every horoscope column is a faint echo of an ancient effort to bring order to the wandering lights. Egyptian priests used Sirius to anticipate the Nile flood. In ancient Egypt, the annual flooding of the Nile was a matter of life and death. It brought water and fertile silt to the fields. Without it, crops could fail. One celestial event became especially important. The star Sirius returned to visibility just before sunrise, after being hidden in the sun's glare. This heliacal rising happened close to the season when the Nile flood began near Memphis in earlier periods. Egyptian priests watched for it with great attention. The star's return became associated with renewal, abundance, and the start of the year. This connection between sky and river helped shape one of the world's great agricultural civilizations. The wonder lies in how a star and a flood became linked in human understanding. A bright point above the horizon could announce a transformation on Earth. It was not magic in the modern sense. It was pattern recognition across time. The Egyptians learned that the heavens could help them prepare for the river's gift. The Antikythera mechanism modeled celestial cycles with bronze gears. This object was found in a shipwreck near the Greek island of Antikythera, and it changed how scholars imagined ancient technology. At first, it looked like corroded fragments of metal. Later study revealed something extraordinary. Inside were gears, inscriptions, and mechanical relationships designed to calculate astronomical cycles. The device could show positions of the sun and moon. It could predict eclipse seasons. It also included calendar functions connected to Greek timekeeping. Nothing else from the ancient world has survived quite like it. Its craftsmanship suggests a tradition of precision engineering that must have been more advanced than the surviving evidence once implied. Imagine turning a handle and seeing celestial rhythms expressed through interlocking teeth of bronze. The sky was being translated into machinery. This was not a telescope, and it did not magnify anything. Instead, it made time itself mechanical. The mechanism proves that ancient astronomy was not limited to observation. It could also become an intricate model you could hold in your hands. Hipparchus discovered Earth's slow wobble by comparing star positions. Hipparchus was one of the great astronomers of the ancient Greek world. His achievement came from noticing that the heavens were not quite as fixed as they seemed. By comparing his own observations with earlier records, he found that the positions of stars had shifted slightly relative to the equinoxes. This led him to identify what we now call precession. Earth's axis slowly wobbles, like a spinning top moving under a gentle pull. The effect is extremely slow, taking about 26,000 years to complete one full cycle. No single lifetime could watch it unfold directly. That is what makes the discovery so impressive. Hipparchus found a vast motion by comparing careful measurements across time. The stars looked eternal and unchanging to the naked eye. Yet hidden beneath that stillness was a grand celestial drift. His insight showed that astronomy could reveal movements too slow for ordinary perception. It expanded the scale of time that humans could meaningfully understand. Eratosthenes measured Earth's size using sunlight and simple geometry. Eratosthenes worked in Alexandria, a center of learning where reports from distant places could become scientific evidence. He heard that in Syene, near modern Aswan, the sun shone straight down a well at noon on the summer solstice. At the same moment in Alexandria, a vertical stick cast a shadow. That difference mattered. If Earth were flat, the sunlight should have fallen at the same angle in both places. Instead, the shadow revealed curvature. Eratosthenes measured the angle, estimated the distance between the two cities, and used geometry to calculate the circumference of Earth. His result was astonishingly close, depending on the exact length of the unit he used. The beauty of this experiment is its simplicity. A stick, a shadow, and the careful question were enough to measure a planet. No ocean voyage was needed. No spacecraft looked back from orbit. By trusting reason and observation, Eratosthenes turned sunlight into a measuring tape wrapped around the world. Chinese observers kept some of history's longest sky records. For many dynasties in China, the heavens were considered closely connected to the state. Because of that belief, official astronomers were appointed to watch the sky and record unusual events. Their work produced an extraordinary archive. Over centuries, they noted eclipses, comets, guest stars, planetary conjunctions, meteors, and other phenomena. These records were often dated carefully because they mattered politically and ritually. Today, historians and astronomers value them for a different reason. They provide a long timeline of real sky events seen before photography or telescopes. Some entries help identify supernova remnants. Others help track the history of comets or refine ancient eclipse calculations. The power of the archive comes from continuity. Many cultures watched the sky, but few maintained official records across such long stretches of time. Each note may seem small by itself. Together, they form a bridge between ancient court life and modern astrophysics. The sky changed, and someone was there to write it down. The Maya Dresden Codex includes detailed tables for eclipse prediction. The Dresden Codex is one of the most precious surviving books from the ancient Maya world. Its pages carry astronomical tables that reveal an advanced understanding of repeating sky patterns. Among its most intriguing sections are eclipse tables. These did not predict eclipses in the modern local sense with exact maps and times. Instead, they identified intervals when eclipses were likely because the sun and moon returned near the right alignment. The tables show how carefully Maya specialists watched lunar cycles and incorporated them into their calendar system. They used arithmetic to track danger periods across long spans. In a culture where celestial events carried ritual significance, knowing when such events might occur was powerful knowledge. What is so striking is that this information survived in a folded bark paper manuscript. Many Maya books were destroyed after the Spanish conquest, so the Codex is a rare window into a much larger intellectual tradition. Its pages preserve the science of cycles, memory, and prediction. Ancient Mesopotamians treated unusual sky events as royal warnings. In Mesopotamia, the heavens were read as messages from the gods. This belief gave unusual celestial events enormous importance. A lunar eclipse, strange halo, bright comet, or unusual planetary arrangement could be interpreted as a warning about the king, the land, or the future of the state. Scholars gathered these interpretations into omen texts. One of the most famous collections is known as Enuma Anu Enlil. It connected specific sky appearances with possible earthly outcomes. To modern ears, this sounds far from science. Yet the system required detailed observation, careful classification, and extensive written tradition. When the court wanted guidance, scholars needed records. Their religious worldview pushed them to become disciplined watchers of nature. Sometimes rituals were performed to reduce danger. In extreme cases, a substitute king could briefly take the throne during an ominous period. The practice reveals a world where astronomy, politics, and fear were deeply connected. The sky was not distant. It was part of government. Greek astronomers knew planets wandered differently from fixed stars. To ancient observers, most stars kept their patterns. They rose and set together, holding the same shapes night after night. A few lights behaved differently. These were the planets, whose name comes from a Greek word meaning wanderers. They moved against the background stars, sometimes slowing, brightening, or reversing direction for a time. This strange backward motion was especially challenging. Mars made it obvious, but Jupiter and Saturn did it too. The Greeks recognized that these objects needed special explanation. They were not simply stars with unusual brightness. They followed paths that demanded geometry. This problem became one of the great engines of ancient astronomy. How could a universe built on order produce such loops? Different thinkers offered different models, and each tried to preserve regularity beneath apparent confusion. The wandering planets taught astronomers that the sky was not just a dome of fixed lights. It contained bodies with individual behavior. Their puzzling paths forced mathematics to reach upward. Ptolemy's geocentric model guided astronomy for more than 1,000 years. Claudius Ptolemy lived in Roman Egypt, and his great astronomical work became one of the most influential books in scientific history. He placed Earth at the center of the cosmos, as most scholars of his era expected. Around it, he built a mathematical system that described the motions of the sun, moon, and planets. The model used circles upon circles, including devices called epicycles, to account for planetary loops and changing speeds. Its purpose was not simply philosophical. It could generate predictions. For centuries, astronomers in the Islamic world and medieval Europe studied, commented on, improved, and taught his system. Even when later thinkers challenged it, they had to understand it first. Its long success came from its practical power and mathematical detail. Ptolemy's universe was wrong in its central claim, but it was not foolish. It was a serious attempt to save the appearances of the sky. Its endurance shows how powerful a useful model can be, even before the deeper truth is known. Indian astronomers developed sophisticated methods for tracking planetary motion. Across ancient India, astronomy grew into a precise mathematical tradition. Scholars were not only watching the heavens, they were building calculation systems that could describe where planets should appear against the stars. Texts known as Siddhantas set out rules for predicting celestial positions, using cycles, angles, and numerical procedures. These methods helped astronomers prepare calendars and choose ritual timings, but they also show a deeper scientific curiosity. Planets do not move evenly across the sky from Earth's point of view. They speed up, slow down, and sometimes appear to reverse. Indian astronomers created models to handle those changes with impressive skill. Later figures such as Aryabhata described Earth's rotation as a way to explain the daily rising and setting of the heavens. That idea was bold in a world where most people felt the ground was still. Ancient Indian astronomy reminds us that the history of sky science was not confined to one region. Many cultures were solving the universe in their own mathematical language. The Nebra sky disk may show Europe's oldest known star map. Found in Germany and made from bronze with gold symbols, this remarkable object looks simple at first. A bright round disk, a crescent, and scattered dots appear across its dark surface. Yet those shapes may represent the sun, the moon, and a cluster of stars often identified as the Pleiades. It is more than 3,000 years old, which makes it one of the most extraordinary sky-related artifacts from Bronze Age Europe. Some researchers believe it may have helped reconcile lunar and solar calendars. In other words, it may have guided people through the problem of keeping moon months aligned with the farming year. Later additions to the disk appear to mark horizon arcs, possibly connected with where the sun rose and set at different times of year. Whether it was a scientific tool, a sacred object, or both, it reveals a society thinking carefully about the sky. The disk feels like astronomy held in the palm of a hand. Egyptian temples were often aligned with sunrise on sacred dates. In ancient Egypt, a temple was not only a building, it was a carefully placed meeting point between the human world and divine order. Many temples were oriented so that sunlight entered in meaningful ways at particular times of year. A ray at dawn could travel through a doorway, cross a hall, and illuminate a sacred space. This effect was not accidental. It required planning, observation, and architectural precision. The date might relate to a festival, a royal celebration, or the worship of a particular deity. When the sun appeared in exactly the expected place, it confirmed that the temple stood within a cosmic pattern. To witness such a moment must have been powerful. The stone itself seemed to awaken. Modern visitors may admire columns and carvings, but the original experience also involved timing. The structure was designed to work with the sky. Egyptian sacred architecture turned sunrise into a recurring event of meaning. Babylonian clay tablets preserved centuries of planetary observations. Clay may seem fragile, but when baked by sun, fire, or accident, it can outlast empires. That is why so much Babylonian astronomy survived. Scribes pressed wedge-shaped marks into tablets, recording dates, positions, appearances, and celestial patterns. These documents were not casual notes. Many belonged to organized traditions of observation and calculation. Over generations, the records grew into a vast archive of sky behavior. A planet's position on one night might mean little by itself, but thousands of such entries could reveal patterns too slow for one person to understand. The tablets also show how astronomy depended on institutions. Temples, courts, scribes, and scholars all helped preserve the work. When modern historians read these marks, they are not just reading ancient language. They are hearing the rhythm of repeated watching. A hand pressed wet clay after a night under the stars, and that small act carried planetary knowledge across more than 2,000 years. Ancient sailors used Polaris before compasses reached common use. At sea, the horizon can erase almost every landmark. This made the northern sky especially valuable. Polaris sits close to the north celestial pole, so it appears nearly fixed, while other stars circle around it. For sailors in the northern hemisphere, its position offered a dependable guide. By finding it, they could estimate north and keep a course through darkness. Its height above the horizon also gave a rough sense of latitude. The higher it appeared, the farther north a traveler had gone. This was not modern navigation with charts and instruments, but it was powerful enough to support long voyages. The star did not always hold the exact role it has today, because Earth's axis slowly changes its pointing over very long periods. Yet in many historic eras, it was close enough to serve as a celestial anchor. Imagine steering a vessel through black water while one steady point watched overhead. That single light could mean direction, safety, and home. The Dogon people preserved careful traditions about seasonal sky patterns. In Mali, Dogon communities developed rich traditions connected with the heavens. Their sky knowledge has often been discussed in exaggerated or distorted ways, so the real story is worth treating with care. Like many agricultural societies, the Dogon paid attention to seasonal patterns because timing mattered. Stars, rains, planting, and ceremony belonged to a connected cycle of life. Certain appearances in the sky could help mark when activities should begin. Oral traditions preserved this knowledge across generations, not in textbooks, but through teaching, ritual, story, and observation. That makes it different from court astronomy written on tablets, but not less meaningful. It shows another way humans can maintain an understanding of the sky. Knowledge can live in memory when a community values it deeply enough. The Dogon example invites us to remember that ancient astronomy was not always separated from culture. It often belonged inside daily life, where the sky helped people understand time, land, and responsibility. Chinese astronomers described sunspots long before telescopes revealed them. The sun seems smooth to the naked eye most of the time. Yet under certain conditions, especially when haze, dust, or thin cloud reduces its glare, dark marks can be seen on its face. Chinese astronomers recorded such features centuries before telescopes made them easy to study. Their reports described spots appearing on the sun, sometimes comparing them to birds, eggs, or other visible shapes. These observations were carefully noted because unusual solar appearances mattered to imperial sky watchers. Today, we understand sunspots as cooler regions caused by intense magnetic activity. They come and go as part of the sun's changing behavior. Ancient observers did not know the physics, but their records still matter. They provide evidence that solar activity was noticed and remembered long before modern instruments. It is astonishing to think of someone looking through a veiled sky, seeing a dark mark on the brilliant sun, and deciding it was important enough to write down. The moon helped ancient cultures divide time into months. The moon offers one of the clearest cycles in nature. It grows from a thin crescent, becomes full, fades again, and disappears into darkness before returning. This rhythm is easy to see, and it repeats often enough to organize human activity. Many ancient calendars began with lunar months because the moon gave time a visible shape. People could look up and know roughly where they were within the cycle. This mattered for religious observances, travel, fishing, agriculture, and social gatherings. A moon-based month was not perfectly matched to the solar year, which created challenges later. Still, its appeal was obvious. The moon was a clock everyone could share. It did not require a palace, a priesthood, or a measuring tool. Its changing face moved above rich and poor alike. When ancient people counted nights by the moon, they were turning the sky into a public calendar. Time itself became something bright enough to watch. Greek philosophers debated whether the stars were distant suns. To many ancient people, stars were lights fixed to the heavens. Yet some Greek thinkers wondered whether they might be far more like the sun than they appeared. This was a startling idea. The sun dominates our sky with heat and brilliance, while stars look like tiny points. To suggest a connection requires